Let me show you how to be a good Bayesian.
Hello, my dear Bayesians. And in this episode, we're talking about the part of the workflow everyone forgets, actually making decisions. We spend so much time staring at trace plots and checking our priors, but in the end, the goal isn't just to have a posterior or a beautiful model. It's just to use it. My guest today, Daniel Saunders, is a senior data scientist at PyTensor Labs with a PhD in philosophy. And he spent a lot of time thinking about how to turn inference into action. So in this episode, Daniel is going to live demo his new Bayesian decision theory workflow. We'll see how to use PyTensor, which is PyTensor's backend, to optimize for profit and utility instead of just accuracy, and why shifting the focus to business value is the ultimate soft skill for data scientists. This is Learning Bayesian Statistics, episode 152, recorded February 24, 2026.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is the place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all.
Daniel Saunders, welcome to Learning Bayesian Statistics.
Thank you for having me.
Yeah, thank you for being on the show. I'm thinking, but I think you're the first guest that I know already from real life and then coming on the show. Usually it goes the other way around. I know people online through the podcast, and then somehow, because one is traveling, I meet them in real life. But no, for you it was the other way around. So yeah, well done. You're the first one.
Good to be the first of something. We met at a StanCon a couple years ago, I think, over in Oxford.
Yeah, 2024.
Yeah, that was a nice conference. I had a lot of fun there.
Yeah, that was great. Plus it was in Oxford, so that was super fun. Like classic British atmosphere. Very intellectual, of course. So I mean, I don't know for you, but that's my element. I prefer these atmospheres, and so like breaks, and you go to pubs, and you get a beer.
And the bar is like 400 years old, which is a nice touch often.
Yeah. No, incredible. I was very surprised by Oxford prices when I came there. I was definitely not expecting these prices, especially for hotels. But I have to say, I understand why it's so expensive. It's a great place to be in. So
they must be used to having the university's comp hotel stays for all their guests. So
I know.
Paying your own money is a little bit of an anomaly for them.
Yeah, that's for sure. But no, that was super fun. Like I really enjoyed it, and I think it was the first time in my life where I was actually kind of feeling like a celebrity, because the first time when I arrived in Oxford the day before the conference, so like nobody knew me in theory. I was walking down the street in Oxford, just, sucking up the atmosphere. And then somebody stops me and is like, "Hey, sorry, aren't you Alex Andorra?" And I'm like, Well, it depends. What do you want? And it turns out I was a fan of the podcast. And so he was like, well, I love the show. That's great for you to be coming here and so on. So yeah, that was the first time it happened to me. That was pretty fun. So, everybody can be in a celebrity. You just need to find the smallest niche possible. And then boom, that's perfect.
Unfortunately, it might be the only place in the world where you'll get people stopping Bayesians on the street and asking them
For sure.
to confirm their identity.
Yeah. Maybe in Edinburgh, isn't there
Mhm.
where David Hume is? I think maybe also probably where Bayes is in London, the cemetery. I went there last time I was in London. I saw Bayes' tombstone. That was amazing.
Yes, and
But yeah, but I have to say it's good. Like it's the only place, Otherwise, it becomes like I understand why it could be a hassle. You're minding your own business, walking in the street, and then you have to talk to people. Can be. I can see how it can be tiring when it's all year long.
yeah, I think celebrities have a very difficult life in that regard.
Yeah, I'm not sure it's a great. I'm not sure it's a great trade-off. I'd love to be some A/B testing. Honestly, if I could do that, and test that for myself, I'd do it for curiosity. But I think anonymity is a great deal that's often underrated. That being said, we're not here to talk about me. We're here to talk about you, actually. So, and you have a great background. Like, I think it's awesome that you're on the show because you have a PhD in philosophy. So you're definitely the first guest to have that and to have such a focus in philosophy. And you have a focus on logic and decision theory. So it's going to be super fun to talk about. But yeah, like my first question would be, how did you get to Bayesian stats from philosophy? How did that happen?
Yeah, the transition was gradual, but when I was in graduate school for philosophy, during the pandemic, I had a lot of free time on my hands, as many people did. Um, and I also had a lot of time to think about my future in the philosophy field. Um, and started to appreciate that it's like, I don't just want to spend this time acquiring knowledge. It'd be great to acquire a few skills along the way. Um, and incidentally, there's a region of philosophy that's interested in mathematical modeling. They either try and think about the philosophical foundations of it. Models are kind of strange objects where you want to simplify reality. So they're a little bit fictionalized, but they're also supposed to tell you truth about the world. So there's a big philosophy puzzle about how does that work. And then people are also interested in using models to understand how do you make the right decisions, how do societies develop social norms and moral norms. Um, so I decided to head down that direction because I thought it gives me some skills. It's also very interesting. Um, and one of the main stops on that tour was this area called cultural evolution, where they're interested in exactly that question about how do you develop moral norms in a society, what sustains certain moral norms, and what causes norms to change over time. And it turns out that Richard McElrath is one of the kind of major figures in that field. That's where he got his graduate training. And he has this characteristically beautiful textbook about evolutionary game theory and social learning. And so I read that book, loved it, and then was like, hey, what's this statistical rethinking project he's working on? So I got curious enough about that I wanted to learn about it too. And at that point, that was kind of like the middle of my PhD. I was like, I found the thing. I found the thing to really sink my teeth into. So that book was a pivotal period for me. And then I just tried to incorporate kind of Bayesian statistics and modeling into everything I did throughout the rest of my PhD. So I ended up writing about ended up writing a dissertation that explored a few different things, but one of the main themes was about the history of cultural evolution as a field and how do they think about statistical models. And in preparation for that project, I was learning a lot of statistical modeling myself. So yeah, that's the transition. That's how they're so tightly intertwined in my eyes. Well, he seems to have that effect on people. That the particular book has been, everyone cites it as like, oh, this was a changing point for me, and
Mm-hmm.
I was no
Yeah, yeah.
exception.
Well, no, that's very awesome. Well, and Richard, if you're listening, well, thank you so much. It's amazing to have such an impact. I guess. Actually, talking about turning point. Was there a specific aha moment during your academic career where you realized that Bayesian stats was the right framework for the philosophical problems you were tackling?
Yeah, I consider myself kind of a non-ideological Bayesian in that I didn't really fall in love with it because of its like philosophical foundations. There's this whole 100-year-long project of showing that Bayesian rationality is the correct way to make decisions. And you might think that Bayesian modeling falls out of that kind of motivation, that it's about the optimal way to update beliefs and the optimal way to make decisions. But for me personally, I didn't find that as persuasive. What I found really gripping was this whole idea that Bayesian inference allows you to focus on the data generating process. What you need to do to build a Bayesian model is just think really hard about what kinds of causal processes contribute to the phenomena that you're interested in. And then it kind of takes care of the rest. The inference process is not entirely trivial. It can still be challenging, but it's greatly simplified. Whereas with frequentists, there's a whole kind of zoo of different estimators and properties of estimators that one has to keep track of. And I feel like that often adds friction to the process of building scientific models. That once you strip it away, statistics is really fun and intuitive, and it is connected to things you already care about in science, like developing theoretical models about how two processes work. So the kind of connection to my academic work was that cultural evolution theorists will build these simple models of how human societies evolve over time. And that's kind of one flavor of modeling, like the theoretical modeling. And then there's like statistical modeling, which in a kind of estimator language, it can often feel disconnected from that. But one of the things I found disturbing or unusual about scientific practice was that these two types of models were often spoken about and developed in isolation from each other. But I just was like, we're trying to represent one reality. So there can't be that deep of a separation between the two. And I think that's what the kind of the philosophical justification for Bayes that persuaded me.
Yeah, okay. That makes sense. And yeah, I really love that idea of with Bayes, you just have one estimator. Right? It's the posterior, and then you're done. You don't have to learn about all these different zoo of tests and yeah, like in which basically trying to see in which box your use case is falling without mentioning the cases where your use case actually doesn't really fit into any of their pre-existing boxes, and then good luck creating a new box in this zoo. So yeah, like this is to me one of the most interesting parts is that it's just you just have one estimator, the posterior, and then do whatever you want with it. That's so powerful.
Yeah, almost as simple as it could be.
Yeah. Doesn't mean easy, but as simple as it could be. I'm actually something I want to ask you about because I think it's also like in our field in general, what are called soft skills, which I usually refer to as interpersonal skills, which I think is a better way of framing that because, usually soft skills are a bit underrated. I'm curious from philosophy, this is actually something that I was thinking someone coming from that field probably has a better sensitivity to these. So do you think there's at least one soft skill, let's say, from philosophy that you find most undervalued in the data science industry today?
I do tend to think that philosophers are well equipped to think about model evaluation in a way that is often like the disciplinary training of other fields can discourage you from thinking about it very clearly. Because in like classical machine learning, there can be a kind of clarity to model evaluation that is artificial for other fields. They'll try to figure out which model reduces the KL divergence the most, or which model will have the best out of sample predictive performance. And because it's so clearly measurable, you can just run a sequence of models and rank them on this one metric. But I think philosophers are a lot happier with ambiguity, and they're a lot happier with trying to justify the model, not from its performance, but from its assumptions. So I think that the kind of very parametric, very causal approach to modeling that's often popular with Bayesians is something that philosophers are well suited to do. And I also think that in like industry, so now I work at a consulting company that does Bayesian models for mostly private industry. I feel like one of the ways a project can go most deeply awry, the way you can waste a lot of really good technical effort, is when senior stakeholders have a totally different expectation about how to assess a model at the end. There's often this question of like, should we trust this model? Why should we trust this model? And I've just, in the short course of my experience in the private sector, I've noticed that these conversations, if they start off on the wrong foot, if they start off as like, let's find a metric that will tell us what the correct model is, then you can trap yourself. You can trap both the scientists who are trying to optimize for that metric, and then the stakeholders who are disappointed when that metric either doesn't do what everything it's promised, or that their scientists aren't able to hit some target that they've decided. That whole conversation feels like it got started in the wrong place, and maybe a little bit less technicality and a little bit more humanistic kind of approaches to modeling can communicate the kind of uncertainty that we're dealing with when we're building these causal models.
News here on the podcast, but I know you also use that all the time, is Bayesian workflow. You know, this, I think it was even episode 6 of the podcast with Michael Betancourt, where we talked about principled Bayesian workflow. And you work a lot on decision theory workflows. How does this workflow extend or change that traditional Bayesian workflow cycle?
Yeah, I think they are typically fairly separate. And I think the separateness is something that is a virtue of the way I've been thinking about decision theory workflows lately. So the kind of classical Bayesian workflow is an iterative process of refining a model and finding out more about your data generating process and incorporating that back in, and having a variety of prior checks and posterior predictive checks to kind of keep you on the track. The decision theory workflow stuff I've been writing about lately comes out of this observation that in large teams, especially in industrial or business contexts, there's a lot of knowledge you have to have about what are the processes that drive the business, but also what are the kinds of metrics they care about improving, what are their constraints and how they can improve that, what are their different levers they can pull to improve sales or decrease wait times, or whatever it is that the problem they're trying to solve. And it can often be helpful to have separate people keeping track of all of that knowledge, because they are conceptually disentangled. In the kind of like classical Bayesian decision theory, the idea is you have a credence function or a probability function that assigns probabilities to all the different states in the world. And then you have a utility function that says, if any one of those states was realized, how good or bad would it be for me relative to all the other things that could be materialized? So kind of in the foundation, these two things are separate. And if someone gives me a really good posterior, I can optimize using that. But frankly, if someone gives me a bad posterior, I can still optimize using that. And I don't need to know whether, like, exactly how the posterior was generated to develop a good tool for creating inferences on the basis of that. Whatever your beliefs are, we can tell you the best decision conditional on those beliefs. So the decision theory workflow is a kind of set of tools for what to do after someone's developed a good model, or even while they're developing the model.
Yeah, okay. I like that you make them, separate but complementary, because I do agree they are not like they are not completely the same goal and same product in the end, and so sometimes you need just a modeling workflow, and a lot of the times you also need the decision theory workflow on top of that. I'm not aware of cases where you just need the decision theory workflow and not the modeling one, but that probably exists somewhere. I don't think I've ever encountered that. One thing, though, that I think is very important to have in mind and tell the listeners is I think a lot of the time, actually, the need for the decision theory workflow on top of the modeling one is underestimated, where people don't really think they need it, or even they don't even consider it. It's an unknown in a way for them. And I mean, in industry, what I've seen a lot is that often you optimize for metrics like RMSE or MAPE, but in your framework on decision theory, how do you shift the conversation from how accurate is the model to how much value does this decision create?
Yeah, I think that orienting the model evaluation process around decision making can help dispel some of these misconceptions about what makes for a good model. So at the beginning of this conversation, I alluded to that there's this kind of project in philosophy of science that's interested in this puzzle about models. Models simplify reality. Sometimes they introduce these artificial parameters that don't tie on to anything in the real world. Sometimes they introduce explicitly false assumptions because the false assumption simplifies the math in some way that's really productive. And you might be a little bit confused about how does this practice work, because if science is supposed to give us better and more accurate pictures of reality, then what are all these simplifications and idealizations doing in modeling? One of the prominent answers to this puzzle is to say that every model has a purpose, and you only need to figure out whether it's good enough at its particular purpose. So in kind of industry and science, it seems like there are often three purposes: forecasting, understanding, and decision making. And a model doesn't need to be good at all three. In fact, it often can be to its advantage to pick one to prioritize. Very difficult to explain non-parametric models can be great at forecasting, but terrible at informing understanding. If the end goal of the model is to tell you who to draft in an upcoming sports draft, or how much advertising money to put in particular channels, or which discounts you should run on a product, then you only really need to make sure it's making those decisions as well, as good as it can. Um, and that this lets you be a little bit strategic about how you approach model evaluation, because instead of saying R squared must be above 0.9 before we'll accept the model, you can notice that at certain like adding on additional features to try and bump up the R squared doesn't influence the parameters that affect your decision making in any meaningful way. And you can get to a point where you can quantify the cost or value of making your model more complex. You could say, if I added all these features to the model, if we ran the model for 3 hours instead of 20 minutes, it would save you 20 bucks. And I think that's a kind of really powerful way of anchoring these more abstract conversations about model evaluation in something that businesses can respond to.
Yeah. Yeah, that makes a lot of sense. And I really think that this way of thinking makes usually much more intuitive sense to business stakeholders, because you can relate that to actual business metrics instead of just statistical metrics. And this is usually much more valuable and concrete for stakeholders, non-technical stakeholders, but also it's a much more direct thermometer of what a model is actually doing and how it's lifting the bottom line or not. And in the end, this is really what you care about. And on that note, for the listeners who see PyMC or Stan or NumPyro, or any probabilistic programming language as just a way to sample from the posterior, what is the advantage of using PyTensors, which is PyMC's backend, and this is what you're using in your blog post. We'll get to that very soon, but basically you have that new blog post about decision theory workflow out. That's what we're talking about today. And of course, in that blog post, you're touching on PyTensor and symbolic computation. So can you tell us what is the advantage of using that for the optimization side of things? Why can't we, and that's like a follow-up question, but I think it's a good place to ask it. Why can't we just, run scipy.optimize in a loop over the posterior samples?
Yeah, two good questions. So PyTensor is a kind of unusual backend for a machine learning library these days. It has its history in a project that started around 2012 and was officially sunset in the late 2010s. But PyMC decided to revive it because we saw a particular kind of value in the package that wasn't being captured by things like JAX or TensorFlow. And the value is that it gives you a representation of a sequence of computations in terms of a compute graph. And when I first started hearing people talk about this, I found it too abstract to really gather. But if you take a simple computation like 5 times 10 plus 3, in elementary school, you learn an order of operations that says you have to do the multiplication first and then the addition. So you can think about that sequence of operations as a tree, where the leaves of the tree are the 3 numbers, 5, 10, and 3. And then the tree compresses between 5 and 10. And then it compresses again between the product of those 2 and 3. So you get one final answer, which is the root node, and then a kind of branching tree that goes up to the kind of atomic parts, the leaves. PyTensor lets you look at this tree, and it lets you operate on this tree. So you can do things like, I want to replace 3 with a different number. I want to replace the addition operation with a different with subtraction operation. Or I want to kind of extend the tree. I can take the product of some sequence of computations and then glue it into a different tree, and then continue working on that. So that's the kind of big idea behind PyTensor. The reason why this is so powerful for optimization is that it lets you maintain a division of labor in terms of what your modelers are doing and what your kind of decision maker, like the decision makers, the people who work on algorithmic decision making, what do they do? Because the tree gives you a kind of inventory of reusable parts where the modelers can say, here's your price data, here's your sales target, and we're going to fit some function that links the price data to the sales target. The person working on the optimization doesn't need to know terribly much about what the sequence of operations is that connects A to B, price to sales. They can say, I want to start the sequence at price. I want to get to the sales. And then after that, I would like to add on a bunch of extra stuff to this tree, stuff that's specific to my needs. Maybe I need to multiply sales by the unit profit in order to get the objective function I want. The modeler doesn't care about the unit profit, but the optimizer person does. So that's one benefit, is that the modeler can work in isolation and the optimizer person can work in isolation, and then they can quickly glue their parts together by representing the model as a graph and operating on it. The second benefit is that you can turn any section or entire tree into a callable function. And many optimization libraries, SciPy in particular, have been built around being able to optimize arbitrary callable functions. So you extract a compiled, efficient, nice function out of a PyMC model, and you hand it over to SciPy, and you say, here's my inputs, here's my output, find the best combination of inputs. So that, I think, is your first question. But you also asked a little bit about why not do the full posterior as a sequence of SciPy optimization.
Yes.
Yeah.
Exactly.
So you could take each sample and say, conditional on this one sample, what is the best price of my product? The funny thing about that, though, is you would end up with 2,000 different best prices, and you would need another operation to decide how do you decide between those different prices. What's nice about PyTensor is that you can, the kind of natural thing to do there is to take the average of the different recommended prices. What's nice about PyTensor is you can put that averaging process inside the graph. So you can vectorize, which is a kind of efficient way of doing several computations in parallel over your full posterior, and then average the result. So you get what will be either an expected profit or maybe an expected utility. And you ask SciPy to say, what is the best expected utility or expected profit I can get conditional on this full posterior?
Yeah. I can second that. I've done both. First, I was doing it, artisanally with SciPy, and then smart people like Ricardo Vieira, one of the main maintainers and developers, and Jesse Grabowski, they were like, you should probably try and do that with PyTensor. It's going to be much more principled, let's say, and also much faster, because this is vectorized, as you were saying, whereas if you do that with the SciPy loop, for loop, it's going to take a long time. This can be a very time costly process. I've done that a lot, and I'm very happy that you can do that with PyTensor now. So definitely recommend people to try that out. And you have PyTensor's documentation, but also now Daniel's blog post, which is really amazing and shows you how to do that. So definitely recommend you checking that out. Something I was also wondering, actually, Daniel, is how does this framework of optimal decision making, can you tell listeners how it applies to a concrete environment, in industry, let's say an industrial environment? How does that even apply to what listeners are doing in their job day to day?
So it comes up anytime you need to make decisions on the basis of Bayesian models. the kind of popular topics to make optimal decisions for are things like the price or discount of a product, how much to spend on various revenue generating activities. But it also comes up in government context too. So you need to figure out how much electricity you're going to generate for your province or state or country. And it's expensive to generate too much electricity, but it's quite damaging to generate too little. So you need to figure out some kind of way of balancing those considerations. And you're also dealing with uncertainty in how much electrical demand there would be. So this is another kind of context. So the range of applications is huge for this kind of optimal decision-making framework. Kind of nice feature of this PyTensor approach in industrial contexts is, I don't know, kind of what you were saying a second ago about how we've tried it the hard way and now we've tried it the easy way. Is this particular project I've been working on in my job, we have a very large company who sells products in many markets around the world. And we're building by hand a Bayesian model to understand each market. And when we first started doing this project, we would take the important functions and rewrite them in NumPy and try and extract the posterior, stuff it into NumPy and pass that to SciPy to get our decision. And we realized that every single time anyone made a change to any market about how they wanted to model some process, we would have to rewrite the optimizer code. So in terms of the industrial scalability of optimization, I think being able to abstract over computational graphs is super handy because there's a lot less code to track. Instead, there's this portable object that you can know more about it if you need to know more about it, but you can also know less about it if you would rather be agnostic to the particularities of the function that you're dealing with.
Okay, yeah. So good to know I wasn't the only one to do the artisanal SciPy for loop. I feel better. Something I've also seen in my experience working in industry is that it's often easier to explain a prediction to business stakeholders than a utility function. That I can tell you. So I have an idea on how you can answer that, but I'm very curious to hear your articulated answer. How do you sell the concept of optimal decisions theory to non-technical partners who may not care at all about the philosophical and mathematical underpinnings of why that's the optimal decision to make?
Yeah, and both problems are similar. You're often trying to both sell a particular modeling project to non-technical stakeholders, but you're also trying to elicit their understanding of that problem. So in building Bayesian models, that might be eliciting priors from stakeholders, but it also might be eliciting like functional forms that connect inputs to outputs. And then the utility function is also something that needs to be elicited. You need to know what levers can they pull. Are there constraints on those levers, sort of boundary conditions on how much can they put into this lever versus another one? And then all kinds of particularities about their business that, maybe they have a contract that says that they have to buy so much from this particular vendor, so that part is locked in, but this other part is flexible and they're trying to decide which contract to pick up. But fortunately, I think the decision-making stuff can often be easier to elicit because that's the thing that is most front and center in non-technical decision makers' minds. Frankly, is this going to make more money? There's a very simple utility function that just says $1 equals one utility, and let's maximize expected profit. So I think you can, much like in Bayesian models, you can start simple and then add complexity as you learn. You get some feedback about this decision isn't actually possible for us, or maybe they actually care a lot about making at least this much money in the next fiscal quarter, because maybe they need that much money to start some new project they're excited about. So you can slowly get to a more rich and robust utility function through cycles of feedback. In some contexts, the utility function is extremely well defined, and you just need to find the right people to talk to. So in government regulation, in regulated industries, the utility function will often be sort of implicitly written into regulations. Like the power grid has certain responsibilities to the public, and those responsibilities imply certain utility functions or certain kinds of risk tolerance that they're allowed to take. Similarly, the finance department at a large corporation will know exactly how much each additional dollar is worth it to them. So they might have some diminishing marginal utility function that says that the next dollar is worth a little bit less than the previous dollar, and we know exactly how much less it is worth. And if you can get something like that, you get a really powerful and realistic utility framework.
Yeah, I love that. And basically, yeah, making sure to relate that to dollars is usually a good way to have people interested in it, and understand also really what this is all about, and that this is not some just research thing that is cool but not actionable.
Yes,
So
the
it's
universal language.
Yeah, exactly. Yeah. So let's go into your new tutorial now. I think that was a great introduction. As I was saying, the tutorial is called a Bayesian decision theory workflow. Of course, folks, you have the link in the show notes, and I think Daniel is even gonna show us some live stuff today. So if you're listening, this is a part where you might wanna switch to YouTube to see the video. Before we dive into the code, though, what is the scenario you've prepared for us today, Daniel? And why is it a good representation of the struggles that Bayesian practitioners face?
Yeah, I want to pick something very simple, easy to explain, but it has all of the essential ingredients of what you would face in a more complex situation. So we just have some consumer good, and we're trying to figure out what's the price elasticity of that good, and in turn figure out what's the optimal price.
Yeah.
Okay. A price elasticity is usually something like if I cut my price in half, I double my sales, or maybe I get 75% more sales. That's what that metric usually represents. But yeah, that's the setup to the problem.
Okay. Yeah. Perfect. Simple and to the point with some dollar meaning. So that's perfect. So now let's dive into this. What do you wanna show us right now?
So the data is just synthetically generated, but you might imagine a company tried varying its price over time. Maybe they have run their product for 100 days and they change their price once a week. So this is a really good situation for us. We get a lot of information about how does demand respond to changes in price. And the particular function we're going to use to represent sales as a response to price is just some baseline level of sales times a multiplier. And the multiplier is the current price raised to some power. And this power is called the elasticity. So we can imagine, maybe they make 100 sales a day in the absence of kind of like price-related penalties. Maybe that's the intrinsic demand for the good, is that there's 100 people out there who want it. But then if the price goes up or goes down, you can move the demand in one direction or the other.
Mm-hmm. Yep.
Um, to set up the problem, we're just going to pick some arbitrary true parameters, intervene on the model to generate sales data that obeys those true parameters, and then kind of relearn the things we already know, relearn the true baseline sales, and relearn the true price elasticity. The reason why we do this is because we want to capture a little bit of uncertainty, where if we just knew the right answer, there's not really any Bayesian part to it anymore. We could just plug that number in and optimize from there. But in reality, we won't know exactly what these parameters are. So we want to look at the problem as if there's a little bit of uncertainty. So you can see that we recover the true parameters very, very well. The true baseline price or baseline sales is 100, and we get 99.9 with a tiny little standard deviation around it. And the true price elasticity is negative 1.1 with a little bit of variation around it. So we're in pretty ideal conditions, but not perfect information. And if you're building a kind of Bayesian model, classically, this is where you would end. You would have a summary of your posterior, and that would be the kind of answer you get. So this next section is all where the kind of PyTensor and optimization process begins. So to get to something we can optimize, we need to take a few steps. We need to convert sales into a metric we might care more about. If you want to maximize sales, there's a trivial way to do that. You set the price to 0, and your sales will go to infinity on this function. So we don't want to maximize sales per se. We want to maximize profits. So to do that, we'll need something like a unit profit, and we multiply the unit profit by the sales. And what's nice about the unit profit is that as price increases, your unit profit goes up, but as it decreases, your unit profit goes down. So it stops that trivial solution to the problem. And then we can see kind of an initial view of our objective function. If we knew exactly what the parameters were, if we just plugged in those numbers I told you earlier, we would get a surface that looks like this, and you can just grid search on that surface to find out that the absolute best price for maximizing profit is $3.30. So we can use that as kind of a guidepost to see how we're doing. But when we actually optimize with uncertainty, we're not going to find this answer. We're going to find some kind of approximation to that answer. This next business is that we want to take all of the posterior samples and plug them into our graph. So initially, we just have these little random variables at the kind of in the leaves of our graph. We want to strip those out and replace them with posterior samples. So that's what this is one of the values of operating on graphs, and that's what this function does for us. And then if we have our 2,000 or 4,000 samples, whatever it is, we need a scalar goal. We need a single number that we're trying to maximize. So we can take the mean of these samples. And then there's a little bit of PyTensor magic here, which is not terribly great to explain, but the nice bit is that at the end, we can pull out a gradient function and an objective function. And these are things we can actually use to optimize with. This problem is extremely simple. It only has a single variable that you're optimizing. So we don't really need all of the power of SciPy to do something interesting. So if we just grid search over the function, we can get a different surface, which is what does the model think is the objective surface given the uncertainties that it has, and what does it think the optimal price is? So you can see that even though we recovered the true parameters quite clearly, it still recommends a price of around $4, which is quite a bit different than the actual minimum. So a small amount of uncertainty in the elasticity results in a big change in the recommended price.
Yeah, this is super cool. I think this is also super clear. So really, if you're watching the video right now, I'm guessing this is very clear. If you're just listening, this well done. This is a good level of concentration.
So the so now we can show you what it would look like to put this all into SciPy. And remarkably, it's very compact. You just pass in the callable function that you want, and the initial location and the bounds, and you let SciPy know that the gradient of this function is available inside the big objective function. When we compiled it above, we said one input is the optimizable price, and our two outputs are the profit and gradient of profit. So this function has two things inside of it, and SciPy can use both parts quite happily. I'm rather happy with how compact this representation or this way of coding it up is. And you can see that SciPy arrives at the same conclusion. We did the best price conditional on certainty is about $4. So that is the kind of the workflow, the first pass at it. We could talk about a little bit more. We can talk about playing around with your utility function or representing different kinds of risk or risk aversion in the function. But that's the heart.
Yes. So, yeah, thanks a lot, Daniel. I think this was very clear, and I appreciate you going through that live. This is really great. I think all the threads you just mentioned right now are worth talking about, or even illustrating if you have something about that. Yeah, like the different, maybe we can start with the different levels of risk aversions and how that translates into the cost function. If that's something that you're happy with, because like all the threads, the three threads you've mentioned is things I've seen concretely when working on optimization problems.
Yeah, so classically, Bayesian decision theory says you have your belief function, your utility function, you take them, you glue them together, and you take the expectation over that. So you say, what is the maximum expected utility I can achieve? And I think that's fine for decision makers who are risk neutral. If you think losses and wins are equally valuable, or that you're comfortable with uncertainty so long as that on average things will work out, then that's the right decision-making framework for you. And there's a kind of a robust philosophical dispute about whether risk neutrality is like the uniquely best position. But whatever the answer to that question is, people in practice are risk averse, and businesses might have reasons to be risk averse. That might be kind of beyond your control. So you can build in all kinds of constraints and special modifications to your function. And I think this is illustrates this kind of nice division of labor, is that optimal decision making is a complex process, and that you need to kind of cognitively separate it from the modeling part to be able to keep track of everything. So there's a whole family of different ways of handling risk. If we took a look at what the objective function looks like from the point of view of our uncertainty, you realize that at any given price, there's a wide range of possible sales levels you could achieve. And for those listening, visualize a nice inverted convex function that has a big cone of uncertainty around it. You can see that at really small prices, the uncertainty shrinks because you're kind of moving towards that more degenerate case where you know your sales are going to move to infinity. People are going to be buying your product like hotcakes because it's getting closer and closer to being free. And there's like less complexity in the behavior. Whereas on the other side, as you move to higher and higher prices, there's a huge difference between if one person buys it or if two people buy it. And as a result, you get a much wider level of uncertainty in the kind of profit you might expect to achieve. So the different prices are asymmetrical with respect to uncertainty. And you might want to be on the safe side for some reason. One way to be on the safe side is to have any utility function that diminishes at higher and higher profits. So like there's this kind of long-standing idea in social sciences that people who are really rich aren't that much more happy than people who are a little bit rich. Yeah, once you're kind of past the $500,000 threshold, there's not that much more to be gained in happiness. And that's the kind of idea with these exponential utility functions. This is a very popular technique from economics to model diminishing returns in utility for money. So there's a whole family of them, but all of them have the same behaviors that they saturate as you get more and more money. So instead of just taking your profit, you're taking your profit and passing it and calling that the same thing as utility, you can add an extra layer in between your profit and your utility, which is some function that modifies that. And if you pass in this exponential utility, if you insert that into the computational graph, you can get a different utility function. And it gives you a kind of adjustable parameter for risk aversion. The different functional shapes of the exponential utility correspond to different levels of risk aversion. And you can see that when you have no risk aversion, it still recommends a price of about $4. But as you slowly increase this function, this risk aversion, the recommended price drops.
Yeah.
Because all of this stuff in the tail of the posterior that has really high profits but very high uncertainty, it counts less and less for you. So the function isn't attracted to anything with a big tail. It tends to prioritize small-tailed regions. So yeah, this is one common and powerful approach to representing risk aversion. But we also could explore a couple more if we're feeling in the mood for it.
Yeah, so let's do that. And this is awesome. Like, it's extremely practical. I love that. So I've been using also these kind of plots a lot when working on optimization problems like that. So yeah, I think this is extremely valuable because also like the concepts of cost function or reward function or objective function are a bit complicated to understand at first. So I think these kind of plots really help cementing the understanding.
Yeah, exactly. So this first example is just a way of modifying how does money map to utility. And there's a certain sense in which that doesn't represent like a real risk aversion, because it's not the uncertainty that you're worried about. You tend to stay away from high risk gambles as a product of your aversion to, as your diminishing utility to money. But you could try and build like direct risk aversion into your model as well. So there's this popular technique in financial economics or mathematical finance called the mean variance function. And it's really nice. You take the average of your utility, and then you subtract some adjustable parameter times the variance. And this is just intuitively, it's a penalty for large variance solutions. So if you look at the graph that results from that, at zero risk aversion, you get the same price you got before, $4. But as you slide up your risk aversion, you very quickly realize that the recommended function stays very far away from any uncertainty in the posterior and penalizes all of that uncertainty and moves you towards very cheap products that have less uncertainty in their section of the posterior. So mean variance is nice. It's super easy to implement. It's just an extra line when you are saying take the average. You say take the average minus a penalty for variance. And then there's this other idea called conditional variance at risk. And the idea here is you want to protect yourself in worst case scenarios. You say, in the worst 5% of my posterior, what is the best thing I can do? And the way it works is it basically takes a quantile of your posterior. It says, give me the lower 5% bound or the lower 10% bound, and then just treat those posterior samples as something to maximize expected utility over. So you get a similar kind of behavior. When you use the lower 100% bound, it's the same as what you had before. But as you change what bound you're interested in, such that maybe you're looking at the lower 20%, you'll realize that it's just kind of slicing off this section of the posterior and then taking the expected utility over that. And as a result, it recommends a cheaper product as well. Yeah, so if you have the 20% lower bound, it says make your product $2.70.
Yeah. And I love how this is, like, what's awesome is that first, it's extremely practical and actionable. And second, it's also great because you can check your model's results against extremely common business metrics that make sense in your case. And so you can see if the model is saying something that's counterintuitive, you can really decipher much more easily whether it's actually a problem from the model or it's actually something that was undervalued by us before and that the model helped uncover. And this is extremely valuable for that kind of cases.
Yeah, exactly. It's a common problem where you have been doing things one way for a long time. You build up a Bayesian model to try and tell you how to do things. You look at what it tells you to do and you're like, that's crazy. It's so different from what we were doing before. And it's hard to tell whether who's wrong in that situation. Maybe the folk wisdom had some wisdom in it.
Mm-hmm.
And these sorts of tricks, they won't guarantee that you'll result in what you had before, or they won't necessarily bring you closer, but they can protect you against quirks of the Bayesian model, where maybe the result is driven largely by some very high risk, very uncertain, but potentially profitable channel.
Mm-hmm.
And maybe you don't want to put all of your money on that channel because maybe you did model it wrong, and it's worth slowing down before you change the business plan too much.
Yeah. No, completely. Yeah, that's really awesome. Again, I love that you packaged all of that into that tutorial with so many great plots. Anything else you wanted to show us here before stopping sharing your screen, or
No,
something you want to expand on?
This is my story about the value of PyTensor. It's a great package. Here's
That's a
things you
great
can
one.
do with it.
Yeah. Any other topic you wanted to talk about when it comes to let's say not link functions, that's for that's for regressions, but when it comes to cost functions and optimization threats that we didn't pull yet, or concrete advice that you give people when they are working on optimization, something that you usually do that's very helpful?
I don't think I have anything too much to say in general. It's a
Mm-hmm.
huge topic, and I think partly the reason why the probabilistic programming community has focused on how do you build a good model, and then there's a whole other community that is interested in how do you make optimal decisions. These have often stayed a little bit far apart because they are both really big topics and require a lot of knowledge. So the kind of things to Google if you want to know more about this is like linear programming, stochastic programming, nonlinear programming. These are the kind of words that people who research this stuff traffic under. And you'll learn about the appropriate numerical algorithms for certain situations and the way of translating domain knowledge and constraints into programs that you can solve.
Yeah. I mean, and it's also because, well, you need a good model before to be able to optimize. So, like, I think this is also where the bias of the community comes from, where we had to focus a lot on, okay, how do we even get a good model to begin with? And then we'll focus on, okay, what do we do with all these posterior samples? It's great to have them, but how can we optimally use them? Now we're getting there, but yeah, that meant that we had to develop backends that were able to deal with these things in an efficient way, vectorized way, efficient computation, even better if you have it in your model graph. So that's what PyTensor gives you. But yeah, like these things take time to develop, and this is open source, so it can take even more time because people have day jobs. And PyTensor, well, most of the people there do that for free on their free time. And again, a huge kudos to Ricardo Vieira and Jesse Grabowski, who've been blasting through these issues and PRs almost single-handedly and in an incredibly fast and smart fashion. So yeah, like recommend their episode. Of course, they've been on the show before. I'll put them on the in the show notes. But I think that was the end of the live coding part, right, Daniel? So I think we're done for that topic. Or do you want to add one last thought?
Nope, all good there.
Beautiful. Yeah, and then thank you again for doing that. I think it's extremely valuable and great that we have that out there. And actually, we're almost on time. I've been having you here for quite a while, and I don't want to abuse of your time, but I'm also curious. I know you're someone who likes to learn a lot. So what's next for you? What are you excited about learning next?
Yeah, I'm really interested in getting deeper in this area, especially. I think it's such a big, exciting field that I've glimpsed through the door. But if we had developed a set of tools that makes it even easier to take Bayesian models and convert them into optimizable programs, I think that's well worth our investment. And in actual large-scale industrial projects, this approach simplifies things, but there's still so much complexity and challenge around it. So that's one place I would like to really deepen my interest. I've also started to get really drawn to I was telling my fiance the other day that bread and butter kinds of industries have been my interest lately, like electrical grids and prices and getting things from one place to another. Kind of data science that makes the basic engine of society operate. That's what I've been excited about lately. So I've been kind of poking at finance books and supply chain management topics. But yeah, I'm pretty open-minded. I guess the other thing I've been excited about lately is prior elicitation. I had this observation, or I had this pointed out to me by someone, that if you know someone's utility function, you can figure out what they believe. If you know what they believe, you can often figure out your utility function. And I think that as a community, industry scale prior elicitation is not something we've been so good at, but I think there's opportunity to improve there. So I think it's the kind of the nuts and bolts sort of stuff of Bayesian decision making and the nuts and bolts of industries is where my attention is headed.
Yeah, I guess so. I really like that. And I mean, prior elicitation for sure was extremely important, dear to my heart. The Prelis package, of course, spearheaded by, among others, Osvaldo Martin, who's been on the show. Also, I'll link to his episode about Prelis. Really recommend it. This package, I use it all the time when I'm working on Bayesian models. This makes your job much easier as a modeler when it comes to choosing prior. So definitely give this episode a listen and then try Prelis, folks. On that note, Daniel, anything you want to add before I ask you the last two questions?
No, let's go for it, Alex.
Okay, so as you know, as usual, I have to ask you the last two questions I ask everybody at the end of the show. So first one, if you had unlimited time and resources, which problem would you try to solve?
The people working on new inference algorithms, I feel very jealous of them every day because, probabilistic programming, Bayesian methods, they have this kind of tagline that's like, well, if you just think about the data generating process and you know how to convert that into a piece of math, then Bayes takes care of the rest. We both said this earlier on the podcast, and we also were like, in practice, it's more complicated, but in concept, it's that simple. And the practical part is that getting valid approximations of your posterior is still a very difficult thing to do, especially as models get much bigger. All of this business about reparameterizing models or kind of tuning models for effective MCMC sampling, it does feel like I would like to see all of that disappear one day, that the inference algorithms get good enough that they don't really care what mathematically equivalent representation you decide to use of your model. They just do the right thing. Because anytime you're like trying to model something and then your problem becomes thinking about numerical methods and trying to get into the nuts and bolts of that, that means something has gone wrong. You really aren't supposed to be at the numerical level most of the time in your work if you're doing science or industry. So some folks are working on MCMC algorithms that don't need reparameterization. Either they use a neural network to reparameterize the problem for you. So this is a friend of the show, Adrian's big project. But then Bob Carpenter and then my friend Elliot Carson have been working on this alternative version of HMC that can change the step size of your algorithm as it hits more difficult parts of the posterior, and then re-lengthen the step size when you get back to easy parts of the posterior. So these kinds of tools seem really promising, and the sooner we can get them into routine practice, the better, I say.
Yeah, I couldn't agree more. Honestly, I feel the same. Like, this will greatly help Bayesian modeling adoption once we figure this out, like how to basically make sampling as smooth as possible for users. So yeah, like I really can't wait for that. I have great hopes for these neural network based automatic reparameterizations because, well, neural networks are extremely flexible and powerful. So I know there's already a flavor of that with NumPy. If you're using the normalizing flow tuning routine, you can have access to that in NumPy. So in PyTensor through NumPy, which is Adrian Zabel's brainchild of reimplementation, basically, of samplers in Rust. Of nuts in Rust. And yeah, like I know Adrian is doing a lot of work on that, still very actively working on that. Actually, also with Bob Carpenter that you mentioned. So I'm guessing we'll have them back on the show at some point because I know they're working on some very interesting things. So once this is public, very probably we'll get them on the show again. In the meantime, I've had both on the show already, and I've added the episode to the show notes, folks. So if you want to have background about what these guys are doing, definitely give this a listen. This is for sure frontier science, but hopefully this will be on all our machines in a few years, which will be extremely, extremely valuable, as Daniel was saying. And second question, Daniel, if you could have dinner with any great scientific mind, dead, alive, or fictional, how would it be?
I've always had a big soft spot for Herbert Simon. Do you know this character? Yeah. Um, he's he's really fun as a character in the history of science because he was really pivotal in the early stages of AI. Was really pivotal in kind of decision theory and economics, but also like philosophy. He had some of the early work on like causal graphs, some of the earliest approaches to that field. So he's really a kind of polymathic sort of character. He is in touch with his time, but in touch with all of the topics that we still find really exciting and interesting. And there's this little detail I've always found so fun about him, which is that he didn't finish his undergraduate calculus class. He like went to a few classes and he was like, I don't know if it's for me. So he dropped out and he did political science. So as a person who had a kind of humanities background and then pivoted later on, and I think you have a similar trajectory, Alex, of political science to Bayesian stats. He's kind of a fun character. It's like he is able to work with what he had and accomplish a lot. And I think it's nice to know that you don't have to have spent decades under the stack of linear algebra textbooks to make valuable contributions to what we do. So yeah, Herbert Simon would be a great dinner guest.
Yeah, beautiful. Love that choice, Daniel. You're the first to make it, but definitely great one. And yeah, it's great that the useful contributions can come from so many different backgrounds. Makes all of these much more interesting, and all these dinners and beers that we share together much more interesting also, because then everybody comes with a different perspective. So that's also much less boring, which is great. Fantastic. Well, Daniel, I think we can call this a show. That was really fantastic to have you on. It was extremely practical, so I love that. I know my listeners do too. Please refer to the show notes, folks. They are plenty for this episode if you want to dig deeper. Thank you again, Daniel, for taking the time and being on this show.
Yeah, thank you so much. I've had a really great time, and I think this podcast has been such a valuable contribution to our community. So thanks for your work on that end.
Thank you, Daniel. Really, really appreciate it, and you're welcome back anytime. Even before you were kind to the show, like to make that clear. This is not some kind of quid pro quo. Like, we're already welcome back to the show. But yeah, for sure. Awesome. Well, thank you, and see you very soon on the show.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbaystats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbaystats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbaystats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.